They can't play darts.
No, they specifically trained and then taught a certain procedure.
It's funny because I put the game on a slide that was part of a talk that I gave at Gonzaga. So I was wondering if that was one of the PowerPoints that was up directly on that slide.
I'm actually neighbors with the one of the AI guys at Gonzaga. Jay. His last name. I don't know this guy.
I know most of that department. Not someone I know. I know four of their faculty pretty well.
I'll forget his last name.
Two of them graduated from the same advisor / institution that I did within, one was a postdoc while I was there. One graduated the year before I did, and she's now the chair of that program.
Oh, cool.
Yeah. So let's talk announcements, because just like I said yesterday, this week's pretty important. So Thursday, I guess we'll start with assignment due tomorrow, review on Thursday, exam on Friday. And then what I'm assuming, what I'm going to do is tomorrow I will reveal the next assignment, but we will have 2 weeks for it. We're at the point where I'm planning to take the foot off the gas pedal for close to the rest of the quarter. There are 2 assignments left. You'll have 2 weeks for each of them, but the second assignment is a little bit bigger and harder. So the very last one that you do. In fact, each of those problems is going to be worth 20 points instead of the usual 10 as a way to curve people who want to do better on that last assignment and bring up your grade a bit. So there will be a 340 point last assignment.
Do you know when like our test grades and homework grades are due?
I just talked to Dominic. He's had a very busy schedule. He says he's about a quarter of the way through homework 3. And I said, we have an exam this Friday. We need to get those out. He said, all right, in the next day or 2. So we're doing it as quickly as we can. I have game dev grading to do myself. So I would help him out, but I'm about to give an exam in that I can't ask the TA to grade because it's different from anything he's ever seen. So I have to grade that myself.
Hunter's not available for that one?
He's available, but as good as he is basically the ideal TA. I still don't quite trust him to grade the difficulty of the content and that is on that exam. It's just not stuff that he's seen before. If it's a class that he's taken before, like this class, the last time this class was taught, he was the TA for it, I felt okay with that. Dominic has taken this course before, so I'm okay with him taking a first pass at these exams. But if someone has not taken that content, hasn't seen that content, then I'm kind of okay with grading assignments, but exams, I gotta grade those. All right, so that's the upcoming schedule. The gas pedal will be coming off a bit because, as I mentioned to the few of you who were here a little bit early, we're at a pace, we've moved at a pace that's a little bit even faster than I intended. I wanted to move a little bit faster than I had historically so that I could require that second project. And I think I did it a little bit too fast. So now we're looking at probably 3 weeks worth of content left for the last 4 weeks of instruction. So we're probably going to have a little bit of time that last week, which will be good. There will probably be some in-class time to work on projects. We may have the opportunity to go back and just cover some of the interesting material that we skipped over without that being on an exam or relevant to the course. The grading outcomes. We'll find something interesting to do with that time and that is informative and does not make more work. Questions or concerns before we dive back into what we were talking about? All right, we introduced this new class of languages at the very end of last class, this concept of a recursively enumerable language. And we said that this class of language is such that we can either accept or reject, but not both. We've seen this class of language before. We said that something like determining whether 2 grammars represent the same language is the same type of problem. That's a recursively enumerable problem. Because as soon as we find a single string that is different between those grammars, one accepts it, one rejects it, we can say these two grammars don't recognize the same language. But how would we ever answer yes? We would have to iterate every string in the infinite strings that they would both accept, which that process would never terminate. We would just never find the counterexample for why these two languages could be different. They're not, they're the same. We're never going to be able to terminate that process. So that is an example of a recursively enumerable language. So we allow a Turing machine to go into an infinite loop and never halt, and that is okay, as long as it's for one of the two of those. So basically, for every string that's in the language, the Turing machine is going to accept it in a finite number of transitions. And for any string not in the language, Turing machine may halt and reject, or it may enter an infinite loop. We don't define that. Either one of those is okay in a recursively enumerable language. It just means that we can't do much with it. We can't write a program, an algorithm, because that algorithm may never terminate, which is not particularly useful to us. The other class of language is a recursive language. We've seen this before. This is exactly the subset of language that a Turing machine can accept or reject. So this is the same class of language that we could write an algorithm for. You could write a program that would always terminate, that would represent a recursive language. So an algorithm exists for every recursive language because in a finite number of steps, we can either accept or reject for sure. There are no infinite loops on any particular input. We don't specify how long it's going to take to terminate. It could take longer than the Earth has left, and that's okay. It's still within the theoretical definition of a recursive language because it will eventually terminate with an acceptance or a rejection. So a couple questions. Are recursively enumerable languages recursive? Trying to figure out which language class is a subset of the other. Are recursively enumerable languages a subset of recursive languages? Yes, no, no, yeah, that's right.
There's no rejection.
Right. So that's a great point. They are not. If it's recursive, then we can answer yes and no. And recursively enumerable, we can answer yes or no, but not both. So the subset goes the other way. Are recursive languages recursively enumerable? Yes, because to be recursively enumerable, we say it either can halt and accept or reject, or it can go into an infinite loop. And in a recursively enumerable language, we allow it to go into the infinite loop. So recursive specifies two things. Recursively enumerable specifies one thing with an option for the second. One of those options is what the recursive language does. One of the options is not embedded within the definition of the recursive language. So recursive languages are a subset of recursively enumerable, but not vice versa. One thing we might want to do with a recursive language is enumerate it. This says we want to output every string that is in the language. And so we need an enumeration procedure. Using the concept of a Turing machine, how could we define this? The idea is that for any recursive language, we want some algorithm that is going to output every string that this language accepts. Any thoughts on how we could do that within the using a Turing machine? It'll go back to that concept of a universal Turing machine that we talked about yesterday. The answer to this is that we're going to just design a membership Turing machine. The membership Turing machine is going to be able to answer, yes, the string is in this language, or no, the string is not. We need a second Turing machine that we're going to call the generator, and it is responsible for coming up with all possible strings that are in the star closure of the allowable alphabet. Some of those strings are going to be accepted as members of this language, and some of them will be rejected. The generator generates strings. The membership Turing machine decides whether that is in the language or not. Since we know because the language is recursive, it will accept it or reject it in a finite amount of time, we will get to every string that the generator generates. And since it is also a recursive language, we know that it is countably infinite. So we can now generate them. We can come up with a generation procedure that allows us to, if we use length order like we specified last time, we can generate any string in the star closure of any alphabet in length order. So we have a way of generating every possible string in the language, even though it is infinite, which we can then feed into the membership algorithm. And this will just consistently spit out more and more and more strings in the language and more strings that are not in the language. This process is complete because for any string that you would give me, or you could give me, that is possible in the star closure of that language, I can tell you how long you would have to wait until this membership algorithm tells you yes or no to that string. This process will never finish, but it is complete in that it will look at every string eventually. So it acts kind of like a countably infinite procedure. It starts enumerating and creating all of the strings that are in the language. Does that make sense? Anyone have questions on that or confusions, clarifications I can make? I have a hard time looking at faces to tell if that makes any sense or not. Maybe some thumbs, let me know. Somewhere in the middle. Yeah, so maybe I draw this out a little bit. Let's say we have some infinite binary language. Let's say we want all of the strings that have at least 3 consecutive zeros. This is just a regular language, but it's something that a Turing machine could generate. But there are also an infinite number of binary strings with at least 3 zeros as a substring somewhere in that language. So the generator is going to start producing all binary strings of length 1, all binary strings of length 2, all binary strings of length 3. And for each of these, we're now going to feed each of these strings one at a time into a Turing machine membership that is now going to take on the tape of this Turing machine is going to be the algorithm, basically. We're going to write the algorithm that we're going to use on the tape. And we're going to then write the 0. And this algorithm will tell us with this input whether this has 3 consecutive zeros in it or not. Since it doesn't, this is going to get rejected. Once it rejects it, it's going to pull the next string from the generator, and it's going to run the same program on the 1 and find that this also does not have 3 consecutive zeros. This process will continue forever, where we take each one of these strings and determine yes or no to each one of those strings. The theoretical conclusion from this is that any string that you give me that has 3 consecutive zeros will eventually be generated and then eventually validated. There is no binary string that this will fail to get to. So it is a complete procedure because you can't give me a counterexample of some binary string that should be accepted in this language that this process will not generate. And we can guarantee this process because this is a recursive language. We know that this Turing machine will accept or reject in a finite amount of time. It can't go into an infinite loop because this is a recursive language. So we're never going to get stuck on one of these inputs and fail to be able to move on to the next one. That would be what prevents us from being able to complete this process. Does that make more sense?
So is it like you're taking a string that's already been accepted by the algorithm, and then if by some rule of the language, you can add to it and then accept that whole string, is that kind of what's happening?
It's gonna treat each one separately. We're kind of, here's step 1, step 2, step 3, step 4. The first one that's gonna get accepted is all the way down here. And there are more of them will be rejected than accepted, but we will be looking at every binary string up to something that is reasonably infinitely long. As long as it is finitely long, but it doesn't matter, it's unbounded finitely long, we'll eventually get there. So we won't deal with any infinite strings, but that's okay because binary strings are countably infinite, just like the natural numbers, which is why we can map binary strings to the natural numbers.
But then each tape, if once we get down to the 000, that will be like.
Yeah, then that one will be accepted. And then it's put out into this set that is going to define every string in this language of 3 consecutive zeros. Yeah. Usual.
So is the point to get from doing this that the language is recursive?
Yeah, we would, to be able to say that this is recursive, to be able to enumerate and say, can we come up with every string in this language, or a process that will generate every string in this language? That process doesn't need to terminate, but in order to be complete, you can't give me a counterexample of a string that this won't eventually generate. It's an infinite process generating an infinite language, but it will, for any particular string in the language, it'll eventually get there.
So the idea is to have a generator that generates all possible valid strings within an alphabet, and then have some sort of membership TM that determines is this part of this specific language.
Yes, yeah, and that algorithm is specified on the tape as well. So it'll read the algorithm which specifies how its internal states transfer, and then determining whether this is accepted or rejected. All right, so that's the concept of recursive. You can also have the generator write an output onto the memberships tape, which is basically what it's going to do. When the generator generates the next thing, it will then hold its procedure waiting for this membership algorithm to finish. Then it generates the next string and puts it on the tape. And just continues that process forever. Membership writes onto an output track, some other track, every string that's in the language, and then that becomes the set as it is being generated. So we now have a procedure to enumerate any recursive language. We just need these 2 Turing machines, the generator and the membership. And the generator generates, the membership validates, and you have an enumeration of the language. Where it becomes more difficult is trying to enumerate recursively enumerable languages. I'm just going to pause here for a second and see if we can come up with a way to do this. It is not easy, but it is possible to enumerate every string in a recursively enumerable language. But it's going to require some tricks. So remember that for a recursively enumerable language, you're either going to be able to accept or reject, but not both. One of them may go into an infinite loop. And if we try to use the procedure that we just used on the last slide, that means there's going to be some example, some string that is going to cause this to spin forever. And if we try to wait for that to complete, we won't be able to move on to the next one, which you would think would be a death knell to this process, but there is a way to get around it. And we've actually talked about the way to get around it, but not with regards to this. Can anyone think of anything we've talked about over the last couple of days that might be useful? Yeah.
You can write a simple grammar.
If you could write a grammar.
Simple grammar.
Yeah, the issue is we can't necessarily write a simple grammar because a simple grammar represents a class of languages, and there are recursively enumerable languages that exist outside of what a simple grammar can state. It's a great idea. Yeah.
Let's try the forking process.
Forking process?
Where if something's busy and then you're busy, then we just keep adding other ones.
It's very similar to that. We're gonna come up with a deterministic way to do that. So non-determinism would be one way. Unfortunately, we don't really have access to non-deterministic programs since a Turing machine by itself is deterministic by nature, but it's gonna seem very similar to that. So what we're going to do is utilize diagonalization. It's something that we use to show that the rational numbers were countably infinite. But you can imagine now that the generator generates these strings W1 through anything. This is just the enumeration of every string that could be in the language. What we're going to do is simulate the first move on the first string and then stop. We're going to erase the Turing machine, store that off somewhere, and get the second machine, get the second string, and do just the first move on that. Once we're done with that, we're gonna go back to the first string and simulate the second move on that. Then we're gonna come back to do the first move on the third string, then the second move on the second string, and the third move on the first string. Going back, first move on the fourth. So it's very much like that concept of diagonalization. If one of these goes into an infinite loop, that doesn't stop us from looking at every string that is going to terminate. As soon as one of these does terminate, we just remove it from the queue. If W1 spins forever, we're going to be looking at an infinite number of possibilities, an infinite number of simulations on W2 and W3 and W4, even as we're simulating the infinite number of moves on W1. So everything that will terminate does. Everything that doesn't terminate doesn't hinder us. If W1 does terminate after 10 million iterations, we'll always be coming back and simulating the next one. So if it does terminate, we will find that eventually. But if it doesn't stop us. So this process will find every string that does terminate and then be able to accept or reject, or at least accept everything that is accepted, even if some of them that should be rejected because they go into an infinite loop never get there. If it will be accepted, then we will find it and we will add it to the language, to the enumeration of that language. Does that make sense? Yeah.
So what would it look like if W1 wasn't infinite?
So if W1 is infinite, we are still simulating this move on W2, this move on W2. There's always more to parse by the time we get to the next move of W1. So we will be looking at this forever, but it's not preventing us from looking at the next thing. Kind of the same way that when we looked at rational numbers, we found that if we just did this in row order or in column order, then we weren't going to see every rational number. But if we did a diagonalization, then we were able to show that we could eventually see every rational number. We will, according to this method, try every of these infinite strings any number of times. So if W1 does spin forever, this is just a column that will never disappear from this list. If W2 terminated right here after its second move and either accepted or rejected, then we would just remove this column from this process. And we would move from W3 now back to W1, back to W4, etc. So we're going to diagonally continue to look at new strings, simulating the first move of new strings. So even though this is infinite, for any given W out here, W 10 million, doesn't matter, we'll eventually get to its first move. We'll eventually get to its last move if it terminates. If it doesn't terminate, it won't keep us from looking at string 10 billion.
Oh, this is sort of like we process it, then we swap out which string is processing every.
Yes,
single-
every single move.
So
You're
it's like,
swapping out, yeah.
So it's like scheduling within the CPU.
Yes.
So we see every single one it generates, then the ones that are still going, by the time we eventually terminate, we know.
Yep.
What, because we've gone to infinity.
Yes. So this process is possible. That is the key insight. But it is certainly a pain to think about what it would be like to do this in practice, because you're rewriting the entire Turing machine with every single move that you make, which seems silly. But of course, you could, instead of just looking at a single move, you could look at 5 moves and then switch. You could look at 100 moves and then switch. You could look at 1,000,000 moves and then switch. There's nothing that says this has to be exactly one. Yeah,
How would you know if like W2 second move did terminate?
if it did or didn't terminate, if it did terminate,
Yeah.
then the Turing machine would have an answer. You kind of have the same idea of a generator that's producing these new W's, except that now the membership is instead of waiting for termination, it's gonna do some number of moves and then stop. If it terminates, great, we're gonna remove it from this list of strings that we are looking over because we have an answer. If we don't get an answer yet, that's okay, keep it around, we'll eventually come back to it and simulate more of it. So thinking of this now in 2 dimensions instead of 1 allows us now to do the same concept of diagonalization, and it really just comes down to dimensionality. The same reason that when you have a numerator and a denominator, and those can exist in 2 dimensions and you can use diagonalization, if those dimensions can go on forever, then diagonalization will allow you to explore that entire space. So again, this is an infinite dimension. This is potentially an infinite dimension. So diagonalization allows us to explore the entire space. It's a very similar idea to the rational numbers. Doing okay with that? It's a pretty difficult concept to grasp, but once you get it, it makes sense. And it unlocks the ability now to enumerate recursively enumerable languages. If we couldn't do this, this language class would be really boring. We couldn't say anything about it. But because we have this, we can now come up with a membership algorithm for it. We can't really reject, but we can say that we will still build every string that is in the language, and we will eventually have a definition of that language by which one of these terminate and which ones don't.
So this is still definitely dependent on the universal TM and not like a limited.
Yeah,
Yeah.
yeah. There exists a language class outside of recursively enumerable. The first thing that we might ask is, what would be a language that's out there? Something that we can't answer yes or no to. Are we familiar with the twin primes conjecture in math?
That's a
Yeah, so the twin primes conjecture states that there are primes that are 2 apart, like 3 and 5. And if you continue this process, you will eventually see 17 and 19. And continuing this process, it seems to go on forever. But mathematicians don't have proof that either this terminates or that it goes on forever. What would it take in order for us to be able to answer yes, the twin primes go on forever? If we could find some structure to this that we could map to a function that says, yes, this function goes on forever, but it's seemingly random. To anyone who's ever studied this problem, when those occur and how they occur seems random. You'll have twin primes and a little bit later, more twin primes. And you'll have this vast area of no twin primes before another one shows up. And then you wait and then they show up again right next to each other. And then it seems to have no rhyme or reason to it. What would it take to state no? The twin primes eventually stop.
You need to find some terminating number of twin primes, and then you never see twin primes again.
Well, since there's an infinite number of numbers, how would you know it's just not a really big blank area before you see the next? It's really hard to answer yes or no to this problem. And in fact, what would it take in order for us to be able to answer yes or no? It is quite possible, if the twin primes go on forever, that we can't answer yes or no to this problem, ever.
You'd have to prove something about the pattern itself.
Yes, and if that pattern doesn't exist, kind of like, does pi terminate? That is recursively enumerable, because if it terminates, we will know that it terminates. But for twin primes, we have no way of verifying that it has terminated. And in fact, a video that I will show in a day or two will go through the twin primes conjecture and go through the halting problem and talk about some of the issues with math. And one of the fun conclusions from this is that there are problems in math that we will never be able to prove or disprove. And we can prove that those problems exist. We can also prove that we can't prove what they are. It's unknown until it is known. But how would we be able to tell the difference between what is true and not true if we can't prove it's true and we can't prove it's not true? It is either true or not true, but there's no way for us to ever know. Those problems do exist, and we can prove that they exist, which is the incompleteness theory of math, that math cannot describe everything.
At the same time, we don't know if it can't describe everything or not.
Well, we can. We can actually show that we can't describe everything. There are problems that the rules of math cannot construct in order to be able to answer yes or no to.
Think about something else, but then because we can't solve that yet, we don't know if math is consistent or not.
Right. Yeah, the proof comes down to Gödel numbers, and we'll talk about Gödel numbers. Well, you can see it in the video, but it's pretty cool. So those are some examples. But other languages that are not recursively enumerable are something like the real numbers between a lower bound and upper bound. So the real numbers between 0 and 1. So why is this impossible to enumerate? We kind of hinted at this by trying to say that we could try to come up with all strings of finite length, 1, 2, 3, 4, but that won't ever get to the infinitely repeating rational numbers or irrational numbers that go on forever. So we'll start with and use Cantor's diagonalization to show this. So we will start by assuming that we have an infinite countable set, something like the reals are countable between 0 and 1. You can imagine, I'll give you two examples of this. The first one is the reals, and the second one is the power set of a countably infinite set. So imagine that we have every number between 0 and 1 somehow in this infinite list and then we just have an infinite number of these. And these all go on either forever or don't. Doesn't matter, but there's an infinite list of everything, every real number between 0 and 1. How could we prove that this list, even though it is infinite and complete, how could we show that there is a number that is missing from this list?
I think if I remember the proof, if you start at each index and then you add 1 until you're to the end of the list, and you'll have a number that is not within the set.
Yeah, so the idea is now we're going to construct a new number that is not in this. And what is the first digit of this? It's going to be this digit plus 1. Whatever the next number happens to be, you're going to take the second place and you're going to add 1 to it. So it's distinct from this number in this place. It's distinct from this number in this place. Whatever the third digit here happens to be, we're going to add 1 to that. If this is a 9, we can roll this back over to 0. And it will be distinct from every number in the list at that associated position. If it terminates, you can just put any number there and it will be distinct from that number at that position. But now you have stated some new infinitely long number that is distinct from every number in this list at a particular position. So that becomes the proof that this list cannot be complete, even if you state that it's complete. Because we can still generate a new number that is different from everything in this infinite list. Does that make sense? So even countably infinite is not enough. This is uncountably infinite. And something that is uncountably infinite is something that we can't enumerate. It's outside of even the concept of recursively enumerable. We can't use a diagonalization to try to enumerate this because we will never be complete. we could always give an example of a number that is not in this list by this diagonalization. So this is called Cantor's diagonalization. It's different from the other diagonalization that we have done, but this is specifically Cantor's diagonalization. So this tells us that countably infinite and uncountably infinite are different infinities, or they're infinities of different sizes. Because we cannot map a function from a countably infinite set into an uncountably infinite set. No function exists to that mapping. So we have no way to enumerate them. So languages that are not recursively enumerable, there is no enumeration procedure for it. There's no way for a Turing machine to generate everything in that language. We can give an example, if we tried to do this, of a string that the Turing machine would never reach, even if it goes forever. So that's kind of a interesting result. Let's give you the binary version of this, the power set binary version of this. So we know that binary is countably infinite. We can start with 0, 1, 0, 0, 0, 1, and eventually we will get to every binary number. But what about the power set of that set? Now we're going to say we want to come up with every possible set involving some combination of these numbers. So there would be a set that contains just 0. There'd be a set that contains just 1. I wrote a 0, I said a 1. This process would continue forever with every set that has 1 element. But now, what about the set that contains 0 and 1? The set that contains 0 and 0, 0. The set that contains, this process would go forever of everything that has 2 elements in it. This would also continue forever. You can think that you could do some kind of diagonalization through this, but there are still sets that you would never generate from this, because this will never get to any infinite length set, like all binary numbers with a 0 in it, or 3 zeros in it. We would never get to that set in here because it is infinite. So for a similar reason, why if you outline the numbers between 0 and 1, starting with 0.0, 0.1, 0.2, up to 1, 0.00, 0.01, you would never generate anything of infinite length. You would never generate any sets of infinite length with this process. You would need to come up with every possible language that is infinite within this space, and that is not possible. So the power set of a countably infinite set is not recursively enumerable. You can show this the same way that we showed Cantor's diagonalization. And you can say that this set tells us this would be the infinite list of sets, and this is the infinite list of possible strings that are in that set. So maybe this maps to 0 and 1 and 0, 0 and 0, 1. And then a 1 or 0 tells you membership in this language. So this would say this is the set that contains 0 if the rest of these were all 0. This would be the set that contains both 0 and 1, but nothing else. This is the set that contains 0, 1 and 0, 1 and nothing else. You can generate a new string, membership string in this by just inverting this, inverting this, inverting this, inverting this. And you have a new set that is not in this infinitely long list of sets. So it's exactly the same. This is Cantor's diagonalization proof linked to the concept of the power set of a countably infinite set being the example of binary. We would never be able to determine an algorithm for the membership of this language. It's just larger than something that we can represent. Tying this back to the concept of Turing machines and what this means for Turing machines, there are more languages out there than there are possible Turing machines. Therefore, some language out there must not be recursively enumerable, because the limit of what a Turing machine can do is the membership of a recursively enumerable language. If there are more languages out there than possible configurations of Turing machines, then there must be languages that Turing machines cannot accept or reject. So that is wild to think about, that even the concept of a digital computer has limits. There are languages and language classes that we cannot write algorithms to enumerate, to even begin to explore, based on the limitations of the digital computer. They do exist. Limitations exist. That's so cool. Kind of scary, but it's actually quite cool. As exciting as it is in CS1 to see, wow, computers can do billions of calculations per second, and you can write algorithms that solve just about any problem that you could run across in your life, there are still limits to what a digital computer can do.
So the reason for this, the final result here, is because you can make a non-enumerable language.
Yes.
That means that you can't make a Turing machine for it.
To even enumerate it,
Yes.
let alone accept and reduce. Yeah, you cannot even understand what strings are in this language and not.
Right, okay.
Yep.
And double make sure, because this is a deterministic, but I'm guessing the NP equals P question and answer, can you solve this with a non-deterministic Turing machine?
And the answer is still no. Yeah, even if you can fork this any number of times, there are more strings than possible configurations of Turing machines. Even if you can fork a Turing machine into every possible Turing machine, just say, no matter what Turing machine, there are an infinite number of them, but imagine in one step, I could get there. I could have every possible Turing machine. There would be more strings in this language than there are Turing machines there. Even though both are infinite. So interesting other results that we can find. If a language is recursively enumerable, what about its complement? So we have this idea of a universal set, all strings that can be made out of the star closure of anything in that alphabet. Thinking about everything in the complement. So the complement means everything that is accepted is rejected, everything that is rejected is accepted. Except that in a recursively enumerable language, we don't know what rejection means necessarily. It could either be we terminate with a rejection or we spin forever. Does that mean that its complement must be recursively enumerable? And the answer is no. There are examples of complements of recursively enumerable languages that are recursive.
Because the recursion goes on forever, doesn't the complement also have to go on forever?
It's not.
What?
Yeah. You can see the book for the proof of that if you're curious. I can go through an example or two of that. Maybe that's something we can come back to if we're curious to actually see examples of that and see why that is true.
I just think it's interesting because non-countable infinity technically is bounded by two sides, but it cannot be counted. So it's a uncountable bounded infinity.
Yeah. So languages that are recursively enumerable but not recursive, we already talked about this. Let's talk about a new concept called the universal language. The universal language is all possible Turing machines, is basically the definition. So we're going to call this L sub u. This is the set of all binary strings such that you can break down these binary strings into a first part that describes a Turing machine and a second part that consists of a string that is in the language that is, in the star closure of the alphabet that the Turing machine accepts. So you can say basically it's the set of all tuples MW such that M is an encoding of a Turing machine. W is an encoding of a binary string that's accepted by that. Think of this as a language now. What class is this language? Is it recursive? Is it recursively enumerable? Is it not recursively enumerable? How could we try to enumerate all Turing machine string pairs? Every possible Turing machine, every possible string that is accepted by that particular Turing machine. Is that enumerable?
You can't, well, there's a limit to the number of Turing machines, obviously, so.
It's infinite, but there are infinities that are larger than that. We said that we could do something like come up with all binary strings. Some of those would represent Turing machines, some of those would not. Thoughts on this? What language class would you guess this is? Let's see a show of hands. Who thinks this is recursive? Recursively enumerable? Not recursively enumerable? Excellent. Most people have no idea. Let's give you an answer. It is recursively enumerable, but how would we show that? How could we actually go show that given a two-dimensional, all of the possible Turing machines on one dimension, all of the possible strings on another dimension, we'd be able to eventually spit out every possible pair of every machine, every string accepted by that machine. Let's look at the idea of a proof. So we're going to start by constructing a Turing machine called U. This is going to represent the universal Turing machine, and then we're going to use it to recognize this language. We're going to break U down into multiple tapes. What do each of these tapes do in this Turing machine? The first one is the input of encodings of possible M's and W's. Second tape is used to simulate M on W. Third tape keeps track of M's state, initialized with the start state of that machine. Fourth tape is a scratch tape. That scratch tape is just going to keep track of, it's an infinite amount of storage while we do this. So how do we simulate M on W? So you will search the first tape. There's some transition defined on M, which is stored on tape 3. We'll access tape 3 to figure out what does that transition actually do. What is the current tape symbol that's stored on tape 2, because that's what stores W. We then change the contents of tape 3 to record the new state once we know what the transition is. And then we change the tape symbol that's stored on tape 2 based on what that instruction tells us to do. Finally, we're going to be moving the tape head left or right on tape 2 as specified by the transition that is stored on tape 3. And as we do this, we have a full Turing machine emulator. By these rules, by this definition, we're able to simulate any Turing machine string pair. And on a different Turing machine that just has a representation of that Turing machine and string, we're able to determine and emulate whether that Turing machine accepts that string or not. And this allows us, the entirety of this machine, to now, using diagonalization, try every possible Turing machine, every possible string, such that we can now determine all MW pairs such that W is accepted by that machine app. This is a very theoretical idea. No one should ever try to do this. But it is something that we could set up and do. Given machines that are powerful enough, we could make significant progress. We do not have anywhere near that computational power in today's age. So the language that this universal Turing machine accepts is the universal language. And what's fun about this is it actually fully simulates how computers run programs. This is exactly what happens. We specify the associated transitions when we write every line of code that we do, and we feed it to a general computer that's capable of reading that program and executing the instructions embedded within that program. This would be a Turing machine that does exactly that. So this is the first part of a proof that shows that the universal language is recursively enumerable. The second part of this is that we need to show that it's not recursive. That places a boundary on it is this language class, but it's not this language class that's below it. So that's where we're going to pick up tomorrow and talk about as the final period before we review, before we take an exam. Any questions before we head out? Hopefully this has blown your minds. And if not, you've probably seen it before.
I'll look into it some more.
It's tough to grasp, but when you see it kind of from the top down, it's so cool. I advertise this class as kind of a bird's eye view on computer science. What's possible, what's not. Why do the machines that we use work? And what are its limitations? And I think that is a really cool place to be when you graduate, to just understand what are the limits of the field that you study. What can you do? What can't you do? What is the theory behind why we can do what we can do? It's pretty cool. All right, I'll see you all tomorrow. Office hours starting now for anyone with questions.